Hi, making this video makes me nervous. This is a serious and complex video about an electronic topic and I have to do it very carefully. See, it's like you disagree with Stephen Hawking. Who's likely wrong? You are. And now I'm about to disagree with Dr. Walter Lewin. If you don't know Dr. Lewin, he has a PhD in physics. He's a former professor of physics at the Massachusetts Institute of Technology or MIT. He has made many discoveries, has written tons of books, has received many awards for his scientific achievements, has educated thousands in schools and millions over the web through his online lectures. Just check his Wikipedia page. I, on the other hand, have a master's degree in electronics, have worked for a while as an engineer and then turned YouTuber where I constantly get shocked. My mom thinks I'm mostly okay. Dr. Lewin teaches in one of his courses that the Kirchhoff voltage law or KVL doesn't hold true in some cases, and I disagree with him. The rectifier. I tried to contact Dr. Lewin to discuss this, but understandably he doesn't want to talk about it anymore because so many people online have annoyed him with their stupid reasonings. So I humbly make this video hoping that he or some other great professor sees it and tells me what they think about my results. If he's right, more power to him. I couldn't be happier to be wrong and learn something new. Now, what's Kirchhoff voltage law or KVL? I read the definition from Wikipedia as my alibi, which is: the principle of conservation of energy implies that the directed sum of the electrical potential differences or voltage around any closed network is zero. This is also my understanding and how I learned it. If you find any closed loop in your circuit, the sum of the voltages across its components at a given time is zero, adding them up in one direction. This has never failed me. But Dr. Lewin says KVL doesn't hold when there is a changing magnetic field involved in a circuit.
The potential difference between 2 points in a circuit is no longer defined when we have an induced EMF. 2 voltmeters connected to exactly the same 2 points can measure different values.
I leave links to his relative lectures in the description and I suggest you watch them. But let me quickly summarize his reasoning. Imagine we have a circuit like this, a 1 volt supply in series with 100 ohm and 900 ohm. So 1 volt divided by 1 kilo ohm total means there is a 1 milliamp running through the loop, or 0.1 volt here and 0.9 volt there. If we calculate KVL in the loop in this direction, entering positive of R1 we have plus 0.1 volt, and entering positive of R2 we have plus 0.9 volts, and entering negative of the supply we have minus 1 volt, and the sum of all these is zero. Kirchhoff law holds fine here. But let's remove the supply and short it and instead apply a changing magnetic field through the loop coming out of the page. We know that a changing magnetic field creates current in a loop, and according to the Lenz's law, the direction of the current is this way. Let's say at a moment in time the current reaches 1 milliamp, which means we will have 0.1 volt across R1 and 0.9 volts across R2. The sum of the voltages in the loop is not zero, so Dr. Lewin concludes,
so Kirchhoff is for the birds and Faraday is not.
Then Dr. Lewin does an interesting experiment to prove this. He measures across the exact same 2 points in the circuit with 2 different scopes at the same time and shows that each scope shows a different number.
3, 2, 1, 0. Look on the left, there's V1. Notice, it's negative. Look on the right, there's V2. It's about 9 times larger than V1.
He then concludes that in this special case, depending on which way you look at the circuit, you read a different voltage. So this half of the circuit has a different voltage than the other half, which contradicts the Kirchhoff voltage law and it doesn't hold. He then says that it's the Faraday's law that always holds, not the Kirchhoff's law, which is just a special case of Faraday's law. Dr. Lewin says that the 2 points across the wires are electrically identical.
I want you to understand and appreciate that A1 and A2 from an electrical point of view are identical, they are the same.
Because the resistance of the wire is extremely small compared to the resistors, which is true, and also the inductance of the wire is extremely small, which is also true. So the changing current through the wire creates very negligible voltage across the wire, if anything. I repeated the same test and I agree with his measurements but not his conclusions. Let me repeat the test for you. Like Dr. Lewin, I have a coil or solenoid and I'll switch a battery through a 1 ohm resistor over my coil. The resistor limits the current to 10 to 12 amps. The coil creates a rise of changing magnetic fields and settles. And then I have my loop with 1 kilo ohm resistor on one side and 10 kilo ohm on the other side. We can agree the wire resistance and inductance between them is negligible compared to the resistor values. So when I apply voltage in my coil, the magnetic field in it changes like this and settles. The electromotive force or voltage induced in my loop is the rate of change of magnetic flux, and so the induced voltage changes like this. Now I'll measure across these 2 points in the loop using my sense wire that connects to the scope. Notice that I've twisted the sense wire. Having twisted wire is important because say we have magnetic fields coming out of the board. The induced current in the first twisted loop is in this direction, and in the next loop is also the same direction. This means that say in the black wire the current wants to go in this direction in loop 1 and in this direction in loop 2, and they cancel each other. So using twisted pairs makes sure that the voltage and current in the wires are not affected by external fields. Connecting the scope doesn't affect the main loop behavior at all because it has a 100 mega ohm input impedance, so we can safely say there is no loading effect from connecting the scope to the loop where we measure. Now the sense wires are on the 10 kilo ohm side. Ready? Click. See, I have a voltage pulse with a peak of around 25 millivolts. Now all I do is I flip the sense wires to the 1 kilo ohm side of the loop. Ready? Click. There, we have a negative pulse around 1/10 of the first pulse, because although the current in the loop is the same, the resistance is 1/10. What does it mean? We are reading two different voltages across the same spot. Maybe there is voltage across these wires unlike what we thought. I move the sense wires across the loop wire. Let's measure. Click. The scope just triggers a noise. There is no voltage across the wires. So, does it mean that two different voltages from two resistors are applied across the same spot and the Kirchhoff law doesn't hold? I'm sorry, but this is where Dr. Lewin and I part ways. Please don't hit me. Wait, we are not back in old Iran. You can't hit me. Can you? Let me show you. Dr. Lewin's theory is not dependent on the location of the resistors, so let's rearrange them. Here I move the resistors side by side and very close. If I measure across these 2 points, I still read two different voltages depending on which side I do the measurement, same as before. Here I have both my resistors on one side and I'm measuring across these 2 points on the 10 kilo ohm side. There we go. Click. See, we see a pulse around the same size. Now I flip the wire to the 1 kilo ohm side and click. See, I see the same 1/10 pulse like before, so nothing's changed there. But instead, let's measure right across R1 and R2 and both R1 and R2 with minimal localized sensing loops. Here's the voltage across the 10K. Bam! See, it's around the same 25 millivolts. And the voltage across the 1K, the same 2.5 millivolts. And the voltage across both resistors, bam! See, it's actually higher than 25 millivolts. Pretty close to 27.5. So you see that the voltage across both R1 and R2 is equal to the voltage across R1 plus the voltage across R2, which is the same voltage across the loop. This shows that the voltage across the loop is not zero unlike what we thought, but is equal to VR1 plus VR2. The loop is the secondary of a transformer, with the primary being my coil. Dr. Levin's model misses a transformer in the loop, with the voltage across the winding equal to VR1 plus VR2. KVL holds. But then Dr. Lewin would say, "You stupid kid." Well, he wouldn't say that, he's a nice guy. But he would say, if instead of measuring locally like this, we measure across the loop on the other side, we would read 0 volt across the loop, which is correct. So which one is right? Well, let me show you an extreme case. Let's assume our resistors are infinite or open, and so there is no current running through the loop. Now if we measure the voltage across this tiny gap on this side, we see a voltage pulse. Here's the loop with no resistors measuring right across the gap, and we have a voltage pulse. And when we move the sense wires around like this, we see 0 jump. And here I have the same loop with the sense lines running right on top of the loop, and we have no voltage jump, just some noise. Of course, if I make the sense lines a little bit smaller or larger than the main loop, I'll have voltage jumps. So if in fact we have a voltage V across this gap, for reference say 0 volt here and plus V on this side, why do we read 0 volt across the sense lines? Let's take halfway through the loop. If the voltage here is plus V, the voltage here would be half a V. So we have half a V across this half of the loop and another half a V across the other half. There is no current running through the sense lines, so it doesn't matter that they are going to the scope. Both the sense lines and the loop have the same shape and are in the same field, so they behave the same. Which means we have half a V on this sense line and another half a V on the other sense line. So if the voltage of the loop on this terminal is V, it is reduced on the sense line by half a V here, and on the 0 terminal it is increased by half a V here. So you see that the voltage difference between the sense lines is 0 at this point and the scope shows 0. So the entire reason Dr. Lewin was reading two different voltages was due to bad probing. No matter where you cut your circuit, the voltage across these 2 points is always a unique number. The voltage on this half of the circuit is the same as the other half. Well, this looks a bit complicated, but if you look at this half of the circuit, the voltage across this half is V1, which is the voltage across this piece of loop wire, plus the resistor voltage, which is VR1, plus V2 of this piece of wire. Now if you sense it like this, the same voltages of the loop wires are induced on the sense lines, which subtract from the voltage across these points, and all you read at the scope is VR1. And if you sense on the other side, the induced voltages on the sense lines change to match that side and you read VR2. Now you might say this is different than my extreme case because there is current running through the loop. But according to the Lenz law, this current actually reduces the original field, so the induced voltage on the sense lines is less and they end up matching. There were never two different voltages across these points. This emphasizes the importance of proper probing. Now I'm not 100% sure, but if my quick analysis is correct, to measure the voltage across, say, these 2 points properly, the sense lines must come straight together and twist all the way to the scope or meter. And keep your scope probe away too, because even if this loop is close to your fields, voltage is induced in it and will affect your readings. My conclusion? Kirchhoff laws hold and have held nicely for me so far. If you see any discrepancy, it's because you're either missing a component in your model or probing wrong. Have I been wrong before? Well, yeah, just look at my previous videos. Am I wrong now? I don't think so, because science and analysis and experiments support my claim, as well as a bunch of textbooks written by smarter people.
The sad part is that almost all college physics books, Halliday and Resnick, Giancoli, Ohanian, Young and Freeman, they all, when they deal with self-inductors, with solenoids, they all say, let us now use Kirchhoff loop rule. That statement is a crime.
Well, either way, I'm sure the science will win.
Think about this, give this some thought. This is not easy, and have a good weekend.